This video is designed to help you with the operation of completing the square, which is one of the crucial steps in deriving the quadratic formula. But what it is a way of solving a quadratic equation that is sort of without using the formula, but using one of the key principles involved. So let's take an example of x squared plus 2x equals 4. What we have is an equation that is a quadratic, and we could simply factor this or try to factor this, but it doesn't factor. If we subtract 4 from each side, you're going to find that the equation x squared plus 2x minus 4 equals 0 doesn't factor nicely. So what we're looking for is a way to sort of do what's called complete the square, and the goal for that is to set the left side of the equation up as a perfect square. So if you think about it, there is some value that we can figure out that will make this sort of equation that we've just written factor as a perfect square. In other words, it'll be x plus something times x plus the same thing. And what we're looking for is that the outers and inners, when we FOIL this out, gives us this 2x right here. In other words, we want 2 x's out of it. So if we think about that, what that means is what we want is 1x and 1 and 1 in these two spots. And if we FOILed that back out, we would get the outers and inners of 1x and 1x, which add up to 2x. Now what that also means is we have to look at it and say, well, what would that require in this spot right here? What value would need to be there in order for us to do that? And of course, that's going to be 1, because the lasts then produce 1. So what that means is if we add 1 to each side here, we have therefore created a perfect square trinomial on the left side, taking advantage of looking at our patterns. And that means our right side now has increased by 1 as well. So what we have is x squared plus 2x plus 1 equals 5, since we've added 1 to each side. So we can now use our complete the square and then use the square root property that we've used before from chapter 9.1. And what that's going to allow us to do is say that what we actually have is x plus 1 squared equals 5, and take the square root of both sides. Take the square root of both sides, and that's going to give us x plus 1 equals, now we could have had the positive square root of 5. If you square the square root of 5, you'll get 5. But you could also have the negative square root of 5. If you square the opposite of the square root of 5, that's going to also give you 5. So what we want is both of the roots. So when you take the square root, you have to be careful to identify both of the roots, as we've done with the square root property. And now we have a very easy step. We simply subtract 1 from each side to isolate x, and we get x equals negative 1 plus or minus the square root of 5. Now, of course, this is slightly more complicated if x squared has a coefficient other than 1 on it, but this principle will allow us to do what's called complete the square and use our square root property to quickly solve our equation. Let's try a couple more problems on the next slides. So the first thing I want to point out is, no matter what the equation is, let's take an example of x squared plus, I don't know, 12x equals anything. Doesn't make any difference. Let's call it 500. Okay. To complete the square on the left-hand side, what we need to do is we need to look at this number right here and say we need the outers and inners, which are identical, to add up to 12x. So if they're identical and they add up to 12x, then what we actually want is 1/2 of 12 as our desired position in factoring like this. We want 1/2 of 12. So what that means is we're going to actually want 6 in here. And if we FOIL this out, we're going to get 12x for our inners. Because the outers and inners are identical, they must combine or double to make 12x. So this suggests that we can use a pattern for this every time. In this particular case, what this would mean is, of course, when we FOIL this out, we're going to get lasts of 36. So what that means is we're going to actually add 36 to both sides. And once we've added 36 to both sides, the left side will be a perfect square. We'll be able to rewrite it as x plus 6 quantity squared, and that's going to be equal to 536. And we take the square root of both sides, and we're going to get x plus 6, so this is square root of both sides. Square root of 536 is some number. We're just going to write right now square root of 536, but we want both the positive and negative roots. And then we subtract 6 from both sides, subtract 6, and you're going to get that x is -6 plus or minus the square root of 536, whatever that is. It doesn't really matter. You could either simplify it, assuming that it does simplify, and it should. It looks like probably 4 is a factor. So you could pull a 2 out, and you might be able to pull more out. Or you could simply take the square root with a calculator, or just leave it however you'd want. But this suggests that we can use this pattern to use this complete the square idea in every case. Let's take a look at that on the next slide. So here we have a little more general case. We have x squared plus bx equals something. Based on our previous slide, what we really know is that what we want is our outers and inners to add up to b, which means they're duplicates, which means that the outer and inner are actually b over 2. What that means is we can actually do x plus b over 2 quantity squared, and what we're going to do is we're going to get b over 2 if we FOILed this out, b over 2 squared, which means we're going to add b squared over 4 to each side, and that would complete the square. So no matter what b is, you take half of it. That's what you get for the second term in the binomial. And then, of course, what you have to do is complete the square on the left-hand side, which means you need to add something else. You need to add the square of b over 2, which is b squared plus b squared over 4 to each side. That would allow you then to write this, and you're going to get this equals whatever you started with, something, plus b squared over 4. This hopefully will be clear as we do a couple more examples on the next 2 slides. Here's another problem. This time we have a negative sign, which shouldn't throw you off too much. But what we want is for our middle terms, our outers and inners, to add up to 10, and they're duplicates, so we're going to use 5. And what that means is we want x minus 5 this time, because that's going to give us our outers and inners adding up to negative 10x. And so that's going to be x minus 5 squared. And of course, if we FOILed that out, our last term is going to be 25. So we have to add 25 to each side in order for us to have a perfect square on the left side. So we've now constructed our perfect square. Negative 14 plus 25 is 11. So what we have, if we take the square root of both sides, is we're going to get x minus 5 must have either been positive square root of 11 or the negative square root of 11. If we add 5 to both sides, we're going to get both roots or both solutions to this equation, which is going to be x equals 5 plus or minus square root of 11. Let's take a look at one more example where the coefficient of x squared is not 1. Here's another example. So the coefficient of x squared is not 1, which means we simply divide each side by 2 to isolate x squared, or to get the coefficient to 1. What that means is we're going to get x squared plus 3x, be careful there because you need to make sure that you're dividing the whole side by 2, equals negative 7 halves. So what we're now going to do is try to complete the square. So what we need is something that's half of 3. So 3 halves is going to be what we're coming up with. What that means is we have x plus 3 halves. It's not that hard. But of course, when we square this, our last term is now going to be a fraction. And what is that fraction? Well, it's 3 halves squared. So what we're actually needing on this side for it to be a perfect square is 3 halves times 3 halves, which is 9/4. So we're going to add 9/4 to both sides. What that's going to get us is, if we take that a little bit off to the side, negative 7 halves is negative 14/4. So negative 14/4. So negative 14/4 plus 9/4 is negative 5/4 equals negative 5/4. And of course, now we look at this and we say, well, how can a perfect square equal negative 5/4? It can't. And so what this means is we have no real solutions, but it should be fairly obvious that this process would work out just fine by taking the square root of both sides, taking both the positive and negative roots. If it was, for example, positive 5/4 here or whatever, and then we'd be subtracting 3 halves from each side. Let's take a look at one more problem that does have real solutions but is a little bit messier. Okay? So here's one more problem for completing the square. 2x squared minus 10x equals 1. We're going to divide each side by 2 and divide by 2. And of course that gives us x squared minus 5x. Again, don't forget to divide the 10 by 2. Equals 1/2. That's a positive number, so we're in good shape. What we want is, of course, half of 5 as our second term in the binomial. So that means it's going to be 5 halves. Okay, and we're going to square that, which means when we get the lasts, it's going to be the square of 25 halves. So we're going to add, of 5 halves, pardon me. So what we're going to need to do is we're going to need to add 25/4 to each side. Add 25/4 to each side. And once we've done that, we should get that x minus 5 halves squared is 1/2 plus 25/4, which is 2/4 plus 25/4, so 27/4. And we can now take the square root of both sides. So the square root of both sides, and of course we want both the positive and negative roots. So it's going to be x minus 5 halves equals this positive and negative roots of 27/4, which we can simplify to the positive and negative roots of 3√3 over 2. Work on that yourself and you'll see how that cleans up. And of course what this means is we can add 5 halves to both sides and we're going to get x equals 5 halves plus or minus 3√3 over 2. You could also write this, of course, as 5 plus 3√3 over 2. Hopefully 5 plus or minus, 3√3 over 2. Let me clean that up just a little bit. I hope this has made things fairly clear that you can complete the square by making sure that you know that the middle terms have to add up to whatever you're given there. Of course, if it's not negative 10, if it's negative 17 thirds, and life is a lot more messy as far as the fractions are concerned and that sort of thing, but it's still the same principle. If it's 17 thirds x instead of negative 10x, then 17 thirds divided in half is 17 sixths, and that will be your second term in the binomial, and off you go. I hope this has been helpful.